Hello, Algebra 2. Hope you guys are having a fantastic day. Today we're going to finish 3.7, which is all about graphing polynomials. And so I'm just going to give you like two more things to think about. And then with those two pieces, you should be able to at least sketch pretty much any polynomial. Assuming, well, yeah, you know, within the scope of this course. Okay, so we're going to be looking at end behavior, intercepts, zeros, and then today we're going to talk about how multiplicity affects the zeros. But just as a quick review, okay, remember information we need to sketch polynomials, end behavior, right? Your end behavior is determined by your leading coefficient, whether it's positive or negative, and also the degree. Is the degree even or odd? And so that one will be, is it up, down, is it down, up, is it up, up, and down, down, right? And those are determined by the leading term, the leading coefficient, and the degree. Next, intercepts, right? Your x-intercepts are your zeros, your real zeros, and so you set f of x equal to 0 and solve for x. Your y-intercepts, you set x equals to 0 and solve for y. You do need to know what multiplicity is because the multiplicity affects what the graph looks like. So make sure you remember what multiplicity is. Remember that is the number of times a factor can be divided out by the so number of times the factor can be divided out of the polynomial. Blech. Can't talk right now. It's Friday afternoon. If you couldn't tell. Yes. How the multiplicity affects each graph, affects the graph, that we're going to talk about in just a minute. We're also going to talk about local/relative, same thing. One word is more formal than the other, but you might see either. And global/absolute, same situation there. Maxes and mins. So we're going to talk a little bit about what those are. So in terms of the maxes and mins, let's do that first. You can have two different types of maximums or minimums. Say, for example, I have a polynomial that looks like that. Okay. My global or absolute maximum is the highest point on the entire function. Okay. So in this case, the global or absolute maximum is whatever this point is here. Global or absolute max. Okay. It doesn't have a global or absolute minimum because it goes down to negative infinity. And so it doesn't exist, or it's negative infinity. So no global min, global max is the highest point in this particular case. Okay, a local or relative max or min is like within a certain space, within a certain area. There's like a maximum or a minimum. So local or relative maxes and mins on this polynomial are here and here and here and here, right? They're also like the turning points where it goes from going up to down or down to up. Okay, there's another way to think of it. There is an official definition, but you probably won't really talk about that much until pre-calc. I care more about the general idea and that you're looking for a minimum or a maximum like within a certain little region. Okay, so it's kind of like looking for a peak of a hill or a valley instead of the highest point of the mountain. So that's what a local/relative or global/absolute max and min are. Okay, so that's going to be a global or local max That's a local min. You can also use the word relative instead. Okay, there you go. All right, multiplicity. How does multiplicity affect the graph? Well, it depends on whether or not the multiplicity is odd or even. So, if the 0 has odd multiplicity, it looks like the 0 of x cubed, right? So x cubed looks like this, right? So it passes through the x-axis. If it's even multiplicity, it's going to look kind of like the 0 of x squared, where it bounces off. I'm not quite touching the x-axis there, but so odd multiplicity goes straight through. Even multiplicity, you bounce. That's long story short. Okay, so I just kind of wrote it out nicely for you. But I wanted to show you this graph. Okay, so I just made up a random polynomial that I graphed. And if you look at the different zeros that I have, okay, or different real zeros, I have an x-intercept there, and there, and there. Okay, my end behavior is up, up, like goalposts, right? Because I'm going up on the left and on the right, which means I have a positive, even degree. And then this information, right, this shows me that whatever that x-intercept is, it has an odd multiplicity. So 1 or 3 or 7 or 21, whatever it is. It's got to be odd because it's going straight through the function. This one is also odd, right? It's going straight through the function. And then this last one, because it bounces off, it doesn't go straight through, is an even multiplicity. Okay, so you can have a combination of both in a graph. Okay, so I just wanted to show you what that might look like. So let's try a few examples, and I'll leave that there for you for a second so that you can take a look at the definitions or whatever they are, explanations. So, example, we're going to just graph this function, p of x, without a calculator. So, put your calculators away. We're going to graph it. A lot of it's going to be a sketch, right? You are not going to know exactly what the maximums are and what the minimums are. You're not going to know exact points, but if you have the y-intercept, you have all of the x-intercepts, however many there are, and you have the end behavior, you have a lot of information. And I don't know why that just happened. Hey! Somebody connected to me! Go away! That was awkward. Okay, anyways. I think Mr. White connected to mine on accident. Anywho. Okay, we're graphing a function. Conveniently, for you and for time's sake, I already gave the function to you in factored form. If it's not in factored form, you have to find the zeros using whatever you were using before, rational root theorem, or in testing the possible rational zeros, and all that fun stuff. But we're going to start just with the basics, so we're going to start with it already in factored form. So, step 1, find the intercepts. Okay, here we go. Intercepts are, now since I already have it in factored form, right, all I have to do is set all of the factors equal to 0 to get my x-intercepts, to get my zeros. So let's write my zeros or my x-intercepts. I set that equal to 0, x minus 4 equal to 0. I set x minus 1 equal to 0. I set x plus 2 equal to 0. And I set x plus 1 equal to 0. Okay, as long as it's in completely factored form, you can do that. All right. Then I get x equals 4. Now you want to keep in mind what the multiplicities are. So x equals 4 only has 1, right? There's only the degree of 1. So it can only be divided out once, which means it has multiplicity 1, which is odd. So that one's going to go straight through. Okay. X equals positive 1 has multiplicity 2. Notice the squared on there. So that's even. So that's going to bounce. The plus 2, x plus 2 to the third, that means the 0, x equals negative 2, has multiplicity 3, which is odd. And x equals negative 1 has multiplicity 1, which is, again, odd. Okay, so I've got my x-intercepts. I'm going to also need my y-intercept, okay, which I just set my x is equal to 0, right, because my y-intercept is where x equals 0. And so I would have my y-intercept is when x equals 0, so I want p of 0, which is 0 minus 4 times 0 minus 1 squared times 0 plus 2 to the third times 0 plus 1. Multiply that all out. I've got negative 4 times negative 1 squared, which is 1, times 2 to the third, which is 8, times positive 1, which is 1. So I've got negative 4 times 8, negative 32. Okay. All right, so I've got my x-intercepts, I have my y-intercept, so that's a good chunk of information. I also need my end behavior, okay, because that's going to determine like where the ends go, and do I bounce below the x-axis or do I bounce like this, okay? So I have to find out what my end behavior is, okay? So what that means is you need to find your leading term, okay? Now, one way to do this is to multiply the entire thing out, which is a pain in the butt, right? We don't want to have to FOIL that much, okay? But kind of the nice thing is, if you just look at the first terms, right? So I'm going to rewrite this again so that we have some more room. Okay, so if I were to multiply this entire thing out, right, I'd have x minus 4 times x minus 1 squared. Now, x minus 1 squared, the highest term is going to be x times x, right? Because I have x minus 1 times x minus 1. So it's really just going to be my first term squared. So it doesn't really matter what's here. My first term is x squared. So then my next expansion, right, x plus 2 to the third, if I were to multiply everything out, x plus 2 times x plus 2 times x plus 2, right, my first term is going to be the highest degree on x, which in this case is going to be x to the third. And if the only number in front of x here is positive 1, then I have 1x raised to the third. If that was like 2x plus 2 to the third, then my first term is going to be 2x times 2x times 2x. So it's going to be 8x cubed, so just keep that in mind for future reference. But in this case, it's just a 1, so I've got an x cubed times some other things, which are irrelevant for my highest degree. And then the last thing I'm going to do is an x plus 1, the plus 1, irrelevant. And so then I can multiply all my things together. And so my first term is going to be x times x squared times x to the third times x. So it actually just ends up being x to the 7th. Okay. So then I want to plot it. I know that I start up and then I come down, and my first 0 is 4 right here, and then my next one is 1, and then negative 1 and negative 2. I go through 4, bounce off 1, down to 32, which is my y-intercept, up through negative 1, down through negative 2, and I end upside down on the other direction because that's what that fits with my end behavior. And then that's it. You can plug in points to get other specific points, like where the minimum is or the maximum, right, or your local mins and maxes. But you just need the general gist of the picture. So yeah, it's like a puzzle, and your pieces should fit. Like your end behavior should match what happens with your x-intercepts. So that should be it. All right, good luck. See you later.